Hi guys, welcome to the third part in this video series on low-level programs control flow theory, and in this part we are going to take a look at the function calls, at how do the function calls look like at the low level. And from the previous video we already know that in order to manipulate the instruction pointer we can use some go-to statements, and after using a go-to statement, the value at the instruction pointer is changed to the corresponding instruction or to the address which corresponds the particular instruction to execute next. So instead of the normal sequential order of execution, we could have make some user-defined sequence of execution using the go-to statement. So that was what the previous video was about, and this time let's have a look at the function calls. And the main difference between the function call and the simple go-to statement is that in the case when the function has been called, the location of the instruction pointer before the jump or before the go-to statement is stored at the stack. So that's the main difference. So the function call consists of two parts. The first part is the go-to statement, which is done implicitly, and the second part is some stack manipulation. So now let's see how this works in some visual manner, as always. So say we have this program here, and the instruction pointer is pointing to the very first instruction in the instruction list, and we execute instructions one by one. The pointer is the value of the instruction pointer is increased until we get the instruction number 4. Until we get instruction number 5. And here, in the 5th instruction, we assume that we want to use some function call. So this call instruction uses the physical memory address as an argument. So basically, if here instead of call we would see some go-to, then what happens? Then the instruction pointer jumps from this particular position to actually this one, and then he would start executing the instructions in label 1. But in this case, in the case of the simple go-to, there is no way to remember the location where the instruction pointer was right before the jump. So the location of the instruction 5, which is cell number 5 basically, yeah, is about to be forgotten, yeah. And in the case of the function call, we want to remember the place of the instruction pointer we are leaving in order to execute some function. And usually when the user calls the function, he assumes that after the function returns, he would continue his usual or casual program flow. So in order to implement the function call, the thing we need, the very basic thing we need, is actually to find a way to store the address of the address stored at the instruction pointer right before the jump. And here where the stack is coming into some use. And have a look at this part. So this is the visual representation of the stack, and this little character here symbolizes some stack pointer. And here it's time to introduce another processor register, which is called stack pointer register. So it's familiar to the instruction pointer register because it also stores the physical memory address inside itself. So before the instruction 5 has been ever executed, the stack pointer points to the very top of the stack, but at the beginning of the program it's usually the stack is usually empty. Yeah. So after the instruction 5 has been executed, well, basically the call function consists of two mini functions. The first one stores the value of the address where the instruction 5 is located at to the stack. So this is known as the push operation. So the address of the instruction 5 is actually 5, the cell 5. So this is the value that we want to put onto the stack while the function call. So before the return from the function, but after the actual call, what we have in our stack, then at the exactly place where the stack pointer was pointing to, we save the value of the address of where to return after the function call is executed. So bear this in mind. And also we have incremented the value of the instruction pointer. So say in cases of recursion, this operation would be performed several times, and for those of you who don't know what is recursion, so that is a kind of a function that calls itself. Well, so until some condition to stop calling itself is reached. Okay, so so after the function call, we have achieved two major things. So the first thing, we have adjusted the instruction pointer, and now it points exactly to instruction 1 of the label 2. And the other thing is, now at the stack, at the very top of the stack, so this cell represents the top of the stack, we have the value of the instruction pointer before the jump. So that's the return value. And now we are actually going to execute instructions at label 2 one by one until we reach the instruction number 6. And the instruction number 6 at the label 2 is located over here. So now the instruction pointer has the value of hexadecimal E. And again, two things happens. The first thing happens is an implicit go-to statement. We can't see it, but this actually happens. So the instruction pointer is now being changed or adjusted, and what it does, so the program looks at the very top of the stack and finds their value. So as far as the return instruction 6 stands for the return instruction, and what the return instruction does, it looks to the stack, to the very top of the stack, and finds their value of where he has to actually go to, and he actually goes to this particular location. So the first thing is done is the instruction pointer has been adjusted again, and we are now at the instruction 5, but well, we have already executed the instruction 5, so we are actually at the instruction 6. It probably depends on the particular implementation of what is the particular address being stored here. So probably the address of the instruction 6 has to be stored here. I'm not sure about this, but that's just the details, and I'd like to tell about the general principle of function calls. So well, let's assume here is stored the next instruction to execute. Well, probably that's true. And now we are at the instruction 6, and just before starting executing the rest of the program, what we actually want to do is to pop the value of the stack. So we have to move the stack pointer to the right again, and here the value might be either it was just before, or it may be just back to 0 or null, or any value. Well, it might be initialized, it might be not. Again, it depends on the implementation. Well, but the stack pointer has returned back, and in case of the recursion, again, the stack pointer is going further to the left, and it doesn't necessarily mean that it goes to the left. I just give this example, which is true for the x86 16-bit rail mode programming and memory mapping. Yeah, so in the rail mode, the stack pointer behaves exactly as shown here. So it goes to the left 2 bytes, because in 16-bit mode we always go 2 bytes. So assume that this cell actually 2 bytes. Well, but in our particular example, it's actually 1 byte. Well, doesn't matter for now. So the stack pointer has been adjusted to the value it had just before the function call. So that's the main thing here. And after, basically, the instruction 6 has been executed, and the next one, and the next one. And now, if the instruction 8 contains the kind of exit instruction, in that case, the program will exit. But if it doesn't, if it's just a normal instruction, that the program would actually go further, and it would go to this label 2. And here some disaster might happen, for it's not really intended to be like so. So let's assume that at the instruction 8 we actually want to exit the program. Well guys, this is it for this video, and I really hope that now it gets a little bit more clear on what's the difference between the go-to statements and the function calls on the low level, as well as how the program's control flow works at this low level. This is it for this video, and see you. Have a good time. Bye.